Okay, we are going to move into lesson 2.4. 2.4 talks about constant acceleration. 2.3, acceleration was not constant. In 2.3, acceleration was changing based on an equation. You had to take the derivative of the position graph twice or the derivative of the velocity graph once for 2.3. So in 2.4, it's very important to note that every problem will have constant acceleration. Please pause the video to read over the different objectives that you will go over. When acceleration is constant, let's make sure we again emphasize that. The average acceleration and the instantaneous acceleration are the same. So we can use the rules together, again, only if it's constant. So let's assume that we have 2 points. Time equals 0. Okay, time equals 0 and our original velocity. Please note that that is time and that is velocity. So I'll just put t and v there so you know that that's our original time and our original velocity. Then we move on in a problem and we see a new time and a new velocity. Again, please remember that average acceleration equals instantaneous acceleration because I am stating for this formula you have constant acceleration. So the formula can be found that you do v minus vo over t minus 0, which concludes that v over vo equals t. So let's over here on the side, let's make a theory that says when we have constant acceleration, it holds true that acceleration equals v minus vo over t. Now that is a formula, but we're going to manipulate that formula a lot by solving for, let's go ahead and just solve for v minus vo. Hopefully you know that that implies if we move the t to the other side, acceleration times time equals velocity minus original velocity. That's going to continue to morph into a lot of different problems for us using our Algebra 1, Algebra 2 skills. From this equation, VO is the velocity at the beginning of the problem, and V is the velocity at the end of the problem or at the end of a certain part of the problem. So fundamental equation number 1 is that velocity equals your original velocity plus acceleration times time. Now if you don't see that, that's right here. If we move this over here, we have a positive original velocity. So that would be a positive original velocity plus AT equaling V. So there's that equation. So those two equations are the same, but this equation is what we consider a little more important. So we can find final velocity given original velocity, acceleration of the particle, and the time of our problem. We can use similar reasoning when looking at average velocity. Again, we're assuming that we can kind of make this play here. So we know that average velocity is x minus xo over t minus to. We will again assume that to is 0, like we're beginning the problem in part. So we can say that average velocity is x minus xo over t because we're assuming to is 0. All right, so this is kind of like one thing. Let's go ahead and bring that average velocity here. Okay, so this is a pretty important formula, but not one of the most important formulas. Okay, the ones that are super important are the ones that are in the box. But what we're going to do is manipulate this one. When you think of the word average, you probably think about adding things up and dividing by how many you have. So if I was going to find the average velocity, I would do my original velocity plus my ending velocity and divide by 2, which is the same as 1/2 and then adding the velocities. So because of these two things, watch what we can do even further. Give me a second to find it. Okay, I'm going to go a little bit further on this one, okay? It follows then that average velocity equals 1/2 times the quantity. Now take a look at this up here. I'm going to replace this V. The V that my right finger is pointing at is going to replace with this equation here that my left finger is pointing at. So VO plus VO plus AT. So I put those two things together. So that still means, following down, average velocity is 1/2 2 VOs plus AT. And one more step down, that follows that average velocity is, let's distribute our 1/2, 1 VO plus 1/2 AT. Okay, so what we're going to do with this is, by the way, a very important formula, and this talks about a certain part in the problem. Go ahead and box this one up. We'll kind of use that in a little bit. I use that a couple of times actually in my homework, and I just kind of assumed it's just average velocity. I want to go over here now, okay? Let me see what I have written for a second. Okay. Now what I'm going to do is I'm going to manipulate this formula. So I'm going to draw an arrow over here. If I move the t to the other side, I have average velocity times time equals x minus xo. Now what we're going to do is replace some more fun stuff. Let me see what we're doing. We have a lot of substitution happening. So what we're going to do is solve this equation for x. So I'm going to write that x equals, if I take this xo to the other side, it's a positive xo plus my average velocity times time. Now what I can do is over here I have this average velocity, there you go. Over here I have this average velocity, right? So you see this average velocity that I'm going to color with this child crayon? This average velocity is going to get replaced with this stuff here. So I'm going to have that my distance at the end of a certain part of a problem is the original distance plus, please replace, VO plus 1/2 AT times t. Now let's distribute this t in. So my displacement at any point in time in a problem is my original position plus my velocity original times my time plus 1/2 my acceleration, constant acceleration, times time squared. That right there is a very important problem because a lot of times problems are going to say, hey, where do you end up at the end of this problem? And as long as you have all this information, you can just plug it in or substitute it in and solve. I'm going to suggest to you that with your t's, you might want to put like a little curly tail on them so you don't mistake them for plus signs. Now, we can also just do some calculus to derive these equations. Those of you who are in calc, you're really going to have a leg up when it comes to derivative time. Do you remember how we talked about the derivative of velocity with respect to time is acceleration? Well, we really didn't talk a lot about too much is how to take integrals, but I'm going to teach you how to now. Let's move that dt to the other side. Okay? So my derivative is my acceleration in respect to time over here. So if I do the integral, now remember, the integral is simply the backwards of a derivative. So the integral of my velocity equation is just v, because it would get me back. It's not the derivative of velocity anymore, it's just velocity. But what you might not know is that my integral of acceleration, we're going to go backwards. Acceleration is constant. So acceleration, we go backwards. So instead of losing a variable, it gains a variable. Okay? And then you divide by the exponent of that new variable. So I'll divide by 1, which is useless. I'll write that on there. So it's like 1 divided by 1, but that's going to disappear in the next step, okay? Oops. I'm going to divide by 1 over 1 since that's technically what you do, but that will disappear because it's just 1. And don't forget, it probably dropped off a constant when we did the derivative. You know, on derivatives, how constants like disappear. So if we're going backwards, we have to say, hey guys, there's probably a constant that was being added. Okay, so that leaves us with velocity equaling AT plus some unknown constant. Well, you know how problems begin at like t equals 0? So what we're going to do is at t equals 0, find VO. So I'll do VO equals A times 0 plus my constant. What that means is that my original velocity, whatever my original velocity would be that magic constant. So when I make my main equation, I'm going to write these 3 dots in math class. Therefore, my velocity, what that means is my original velocity is going to be, or excuse me, my ending velocity is VO plus AT. Now, is it important that you know how to derive that? Well, a little bit. You might want to make sure you look it over and understand the steps. But the most important part is that you understand this equation right here, which we did find in the previous page. The next thing I'm going to do is I'm going to derive another equation for you on this side. This one's going to be a little more difficult. Do you remember that the derivative of position with respect to time gave us our velocity? So what that means is if we move the dt to the other side, I can undo my derivative with an integral. So there's my integral, there's my integral. Okay, so the derivative of x, or the integral of the derivative of x is just going to bring us back to my position equation. But what I need to do with this velocity, I need to plug in this equation. So I hope you agree that velocity is the same as VO plus AT. And that's in respect to time. Okay, picking up where we left off. Okay, I got it. So we do x equals, so VO is going to be a constant. So what we need to do with VO is give it a variable t, and then t's exponent is 1, so we'd essentially do 1 divided by 1 here, but that would be useless. I hope you're enjoying the piano music. And then a is a constant, so this t gets an extra exponent, and the 1 gets divided by that exponent in front. And then there would be a constant added to the back, because remember, constants just drop off. Where's my music? Okay, good. It was like, ask and you will receive. Then you write x equals, oh wait, hold on, time out for a second. Now we're going to look at the beginning of time. So we're going to let t equal 0 so that we can figure out what the constant is. I want to write the word let. Let t equal 0. My piano music is stressing me out now because it keeps going. Oh, there it is. I do VO times 0 plus 1/2 AT squared, so 0 squared, plus my constant. And hopefully what you're being able to see is that, oh, and this would be my original position because time is 0, so put an x sub 0 there. So if we let t be 0, this becomes x, your original x. The zeros cancel out, and you end up getting the constant is my original position. I have got to turn that off because I'm going to go crazy if I don't. There we go. YouTube's arguing with me. I feel like I'm not winning. Okay, so therefore, we've got our little therefore equation. X, my position, is my original position because of the constant. There it is. Plus my original velocity times my time, plus 1/2 my acceleration times my time squared. Ta-da! Thank you, calculus. I know where my pause on my video is, or I would help you. Wow, the struggle is real right now. There it is. Hold on, pausing. All right, 3 really big equations we're going to have. And you could, like, do a lot of algebra to figure these out. P.S. I really struggled with one, but it's okay. We all struggle. I was on a different piece of paper trying to prove them. V squared equals VO squared plus 2a times x minus xo. That's one really big equation. Remember, this is only for constant acceleration, guys. And then x minus xo equals 1/2 VO plus v times t. That's another super important equation. And then the third really big one is x minus xo equals my ending velocity in the time period times my time of that time period minus 1/2 of that time period squared. I would suggest memorizing these formulas, but if you're like, hey, Miss Langeli, did you memorize these formulas? I would say no. All right, these are the 5 most important. Are you ready? Important number 1, x equals xo plus VOT plus 1/2 AT squared. All right, guys, let's finish up these equations. So that is one super duper important equation that you derived. V equals original velocity of a certain point times acceleration through a certain time. That'd be ending velocity of a time interval, and that time interval. Velocity squared of an ending of a time interval equals original velocity of the problem squared plus 2 times the constant acceleration times the ending position minus the beginning position. And the ending position minus the beginning position equals 1/2 the original velocity of the problem minus the ending velocity of a time period times that time period. And then the last one is the final position minus the original position equals the final velocity for a time frame times that time frame minus 1/2 the constant acceleration of the problem times the time frame squared. Something important to note over here is, like, it's okay if some information is missing from a problem. So for example, the top problem, the final velocity of a time frame is missing. In the second one, the displacement of the problem is missing. So delta x is missing. Like, in other words, you have no idea how far you traveled, and it's not something you need, so you can use that one. And the next one is the time interval missing. If the time interval is missing, you can use this equation. This one is if the constant acceleration is missing in a problem. You can use this one. And the last one is if they do not indicate what the original velocity of a problem is. Again, these are only for constant acceleration. All right.